In this lecture, let's understand another primitive data type of Rust, that is arrays. An array is a data structure that holds fixed number of elements of the same data type, meaning that the size of an array must be known at the time of compilation and cannot be changed once created. That means cannot be changed dynamically during runtime of the program. This is the syntax of how you can define the array in your program. So again, start with the let keyword and the variable name. This is the name of the array, and you can mention the type after the colon if you want. So it is actually optional, and if you want to mention the type, you should also mention the size, and the type and size information must be separated with a semicolon, and these information must be inside these brackets, square brackets. Size means number of elements in the array, and set of initialization values. The initialization values must be inside the square brackets, and each value must be separated by a comma. Now let's see how to create an array. So first we'll create an array without annotating its type. So we have to use the let keyword. Let me call the array name as my array is equal to, let's say I want to create array of float values. So let's say 2.5, 4.0 and 3.8. So here the type of the array is not mentioned, and it is inferred by the compiler automatically by looking into these values. So type of the array will be here. Basically these are double values or values of type F64. Hence the type of the array will be, in this case, F64 semicolon. How many items are there in the array? 3. So that is length of the array or size of the array. This is the type of this array. So you can also explicitly mention that if you want, like F64 semicolon 3. Suppose if I make this size as 4, then this is a wrong code, because there is a size mismatch, as you can see, mismatched types. Basically what we are saying here is this array is of this type, but this value is of type this one. Hence there is a mismatch. And most of the time you need not to mention the type of the array, because anyway it will be inferred by the values which are used to initialize this array. That's how you create an array. You can also create array of, let's say, characters. Like I can create array of characters like this, plus, minus, something like that. What is the type of this array in this case? So the type of array is char. It's char. These are character literals, semicolon 2. That's the name of the type of this array. As you can say, it's a legal code. And please note that in Rust, it is not possible to use a variable to specify the size of an array at runtime. The size of an array must be a constant expression known at the time of compilation. Since size of the array cannot be modified at runtime, Rust does have a dynamic alternative to arrays called vectors, which can change in size during runtime of the program. Vectors are implemented as a wrapper around dynamically allocated array and provide methods to push and pop elements as well as other useful functionality. So in Rust, you can use vectors if you want a dynamic array. What's the type of this array? Here you can see that the type is not mentioned, but the compiler can infer the type of this array by looking at the left hand side. And here you can see that one of the element in this array is of type U8. So this is suffixed with U8. Hence all these elements are of type U8, because array is actually the collection of items of the same data type. Hence the type of this array will be U8 semicolon 5. Now let's see how to print an array using println macro. So if you try to do this, then you would see an error. This format specifier cannot be used to print the array information. If you want to print the array using println macro, you have to change this format specifier to this. So you have to use colon question mark inside this curly braces. If you're wondering why you cannot print this array using this format specifier, the reason is when println sees this format specifier, it actually invokes the display trait implementation of the argument type. So let's say you have got, instead of this argument, let's say you have got I32 type, a number, let's say. So I32 type actually implements the display trait of the Rust programming language offered by this module, standard format. Let's see that implementation by going through the documentation. Let's say in the documentation, let's search for I32, a primitive data type. And here, if you just browse through this, and if you go to the trait implementation, you see display trait implementation. So here it is. And under this trait, this type implements fmt function, which formats the argument and takes care of printing. And this type also implements the debug trait. But in the case of array, so let's search for array. And in the array trait implementation, so you don't find display, you only see debug. And the debug trait implementation of this type implements the fmt function. That means the debug trait implementation of this type knows how to print it. And the way you invoke the debug trait implementation of any type is by using this format specifier. That's the reason why you have to use this format specifier. In summary, this invokes the display trait implementation. So this invokes the debug trait implementation. Since the array type doesn't implement display trait implementation, you cannot use this. So there is one more type of creating an array in your program, that is using repeat expression. Let's say you want to create an array and initialize all elements to 0. Then you can use value and repeat expression syntax, something like this. Here, this is v, this is n. This value is repeated these many times. And again, this is optional actually. You need not to write this. Now you may be wondering, so how do I create an array without initializing it? For example, let's say I want to create an array of, or let's say I want to create a 1 kilobyte buffer and initialize all values to 0. So I cannot create initialization values using this method, because for 1 kilobyte it will be a tedious job. So I cannot enter 1024 zeros here. For that, we have something called a repeat expression. Let's say I want to create a buffer of 1 kilobyte and initialize all values to 0. So that I can easily do something like this. I will just write buffer and I will use something called value and repeat expression. So the value I want to initialize with is 0. So I'll write 0. Then I'll give a semicolon and then I'll mention the size 1024. This will create an array of 1024 I32 values, because this by default to I32. I'll just mention a suffix here U8. Now this becomes 1 kilobyte buffer and every element is actually initialized to 0. How do I print this? So print ln, you can use the debug trait using this syntax, this format specifier, and then print this buffer. Now let's see another example. Let's say I want to create array of 10 elements and each element is initialized to a value 4.5, let's say. Then I can just write something like this. So this is what we call as value and repeat expression. This is a value and this is a repeat expression. Now array indexing, which is very simple. Please note that the array indexing starts from 0. So this is 0th index, first index, second, third, fourth. And if you want to extract the value of index 3, for example, then you can write something like this. This actually gives the value of the fourth element. And this is a immutable array. You cannot do something like this. So this will be an error because this is immutable. And if you want to change the contents of the array, then you have to make it explicitly mutable by using the mute keyword. I hope you understand this. And now let's see iterating over an array. Here is a program which adds all the elements of the given array and prints the result. So now let's see how to iterate over an array. Now let's code this program. Here I have an array and I want to print the sum of all the elements of this array. Basically, I have to iterate over this array and I have to fetch the elements and add them. So I don't want to modify the content of this array. I'll just take an immutable array. So I need not to mention the mute keyword here because, as I said, I'm not going to modify this array. Now let's create one variable, sum is equal to 0. This is to hold the sum of all the elements, and for every iteration I'm going to add every element to this sum. Hence I'm going to modify this variable sum, hence it must be mutable. So I'll make this as mutable. I have not yet covered looping in Rust. I'll cover that a little later, like different looping methods in Rust. But there is something called for loop, which we can use to iterate over this array. So I'll use the for loop for every element E in, basically it's a for in syntax, for every element in this array. So let's write that array name. For every element in this array, I'm going to add the value of that element to sum. Sum is equal to sum plus E, or sum will use a shorthand notation, sum plus is equal to E. Very simple. And then we'll print the value of sum. As you can see, I have not mentioned any kind of data types in this program. So nowhere the data type is mentioned. We'll see the result. It prints 297. What's happening here? Let's see. For every element in my array. So basically I can directly use this my array in this for loop. So here what happens in this loop is, for every iteration E will take the value of these elements. During the first iteration, E's value will be 10 and 10 gets added to the sum. For the next iteration, E copies the value, this one, like that. So E is called as a loop variable. It could be anything. It could be I or J or N. It could be anything. It is called as a loop variable, and its type is type of the element. What is the type of the element here? I32, right? Then what is the type of the array here? It is I32. The length is 8. So this is the type of the array, and type of each element is I32. You need not to mention this actually. Hence the E is a loop variable and its type is I32, and the sum variable is also of type I32. That's how everything works here, even without using any kind of type annotations. Alright, so now we understood about the array, which is actually a data type where the elements of the array are placed in the contiguous memory locations of the memory, right? So whenever we find data which is stored in the contiguous memory locations in the memory, we can also talk about another data type called slice. Now let's explore the slice data type in Rust. In this lecture, let's understand a slice data type. So it is one of the very important data type of Rust programming language. What is a slice? A slice in Rust is used to reference a portion of an array, but they can also be used to reference other types of contiguous data structures, such as a string or a vector. A slice is nothing but a reference to a portion of contiguous data structure. A slice provides a flexible and efficient way to work with subsets of data and is commonly used data structure in Rust programming, so we'll see that how. But to understand slice, you have to first understand how references work in Rust. So as I said, a slice is nothing but a reference to a portion of contiguous data structure, such as array or string. That's why understanding how references work and how they are used in Rust can give you a better understanding of how slices work in Rust. And that is why first we'll understand a few things about references. Reference in Rust. A reference in Rust can be thought of as a pointer in C, in the sense that it refers to the memory location of a value. However, Rust references are very different from C pointers in several important ways. First of all, references are immutable by default. So constness is by default and cannot be null, and it will never dangle. The borrow checker ensures that the reference will only be valid for the lifetime specified and will not outlive that lifetime. Now let's understand references with one example. Let's say I have a value which is initialized to 42, let's say. So this is actually integer type data. Now I want to create a reference to this value. A reference is nothing but it's like a pointer. So let's say I'll create one more variable, ref of value, and I'm going to use the ampersand sign with this value. Basically, it's like I am storing the address of this value in this variable. In C, you could call something like a pointer. So you will call this as a pointer because it is storing the address of this variable value. In Rust, we call it as a reference. This is how the memory representation of these two lines would look like. Basically, these two are local variables, so they are created in the stack memory. So somewhere in the memory, let's say at memory location 0 cross 200, some hypothetical value, let's say. So 0 cross 200, this variable gets created. Let's say 42 is stored at this location and its variable name is value. And somewhere in the memory, this variable gets created. Let's say at 0 cross 400. This variable gets created, and what this memory location holds is address of this variable, that is 200. That's why we can say visually this points to this because it holds the address of this variable. So we call this as a referent and this as a reference. This is a referent and this is a reference, or we also call it as borrower. We'll see about that a little later. And this is also called as immutable reference because by using the reference, I cannot modify the value of this referent. Hence, this is also called as immutable reference. The takeaway from this slide is very simple. This is a reference because it holds the address of this referent. Now let's get back to this code. What is the type of this variable? Very simple, i32. So what is the type of this variable? It is a reference to i32. That's why ampersand i32. I hope you understand that point. The type of this is this one. Now we'll use the println statement. Let's say I want to print the value of the referent using the reference. So I need to dereference this using this asterisk symbol. It is same as in C. So this is a dereferencing operation. What do you think what this would print? This would print 42, correct? Let's run this. So that prints 42. We'll again call this function without giving this asterisk. What this would print? So do you think this would print the contents of this variable? That is the memory location of this variable. Let's see, let's run this code once again. As you can see, it doesn't print any memory location value. Here the result is quite surprising. So here it was printing 42, that's okay. But here we are not dereferencing. We are just trying to print the value of this reference, but it is actually printing the value of the referent. Here what's happening in this code is the Rust compiler is automatically dereferencing this reference, and it is calling the display trait on that. That's why you are getting this reference value. So you can also call it as a automatic dereferencing. This is a manual dereferencing, so you are explicitly mentioning the asterisk here. This you can consider it as a automatic dereferencing. But how to print the value which is stored in this reference? As we saw in this diagram, basically reference stores a memory address, which happens to be the memory location of the referent. How to print this value? For that, you have to slightly change this code. You have to change the format specifier, that is :p you have to mention. So now this will print the value inside of this reference, which happens to be the address of the referent. Let's run this. This is a real memory location address of the referent value. Then how do I print the memory location address of this reference itself? You can do that. So you can just mention ampersand here. Which actually gives the memory address value where this reference variable is stored. I hope you get the idea. So basically, if you want to print the memory location addresses, you have to use the format specifier :p. This is the equivalent code in C. This is an immutable variable that we can guarantee by using a const keyword in C, and this is immutable pointer. In C, if you want to describe that, then you have to use the const keyword at the pointer side as well as at the data side, like this. So here the value of the pointer cannot be changed. Also the value of the referent, this is a referent, cannot be changed by using this pointer because the value is also constant.